This is the introduction to Experiment 7 for Chem 300, Vitamin C Determination by Redox Back Titration. This is the second week in a row we're going to do a redox titration, but the data analysis for this one is going to be a little bit different. The goal for this experiment is to determine the mass of vitamin C in milligrams in a commercial vitamin C tablet. The method we're going to use is a redox reaction with iodide and sodium thiosulfate. The reactions of interest are shown here. The first two apply to the standardization only. The third one, which involves the ascorbic acid C6H8O6, additionally applies to the unknown determination. This is again a reaction in which one of the participants is the indicator. In this case it's the triiodide ion. It will be present. It's a dark yellow color, and as the reaction proceeds it will be reacted away. And so the endpoint will be the absence of that color. The unknown that you're going to get is a commercial vitamin C tablet. You don't have to dry it, but you do have to crush it up and dissolve it in water. To make your titrant, you're going to use a different kind of balance this week. This is a top-loading pan balance. The reason we use it is because it has a much higher capacity. And we don't actually need the precision that we get from an analytical balance to make this titrant solution. So you're going to weigh out a little less than 9 grams of your sodium thiosulfate. You're also going to add a little bit of sodium carbonate as a buffer. You're going to make your potassium iodate solution. So this is KiO3. This will be in your weigh bottles from last week when you come in. You're going to weigh out the appropriate amount into a 150 ml beaker, dissolve it in a little bit of water, add this to a 500 milliliter volumetric flask, and then dilute to the mark. This is going to be your primary standard solution. You're going to pipette 50 milliliters of it into each of your titration flasks, both for the standardization and the unknown. To each of the flasks, again for both parts, you're going to add potassium iodide, Ki. This will be in desiccators in the balance room. You're going to need about 2 grams for each titration flask. The exact amount doesn't matter, it just has to be over 2 grams because this reactant has to be in excess. Once you add that to the titration flask and dissolve it, you're going to add sulfuric acid, 1 to 4 diluted with water. And when that happens, you're going to form the triiodide ion, which has the dark yellow color seen here. It actually looks more brownish red because there's a large amount of it in this flask. This is what you're going to titrate away, and the absence of this is going to indicate your endpoint. As you titrate with the sodium thiosulfate solution, the solution will pass through this amber color, eventually turning into yellow and then pale yellow. At the endpoint, the disappearance of the pale yellow indicates that there's no more I3-, but that's hard to see. So at a certain point you're going to stop before the endpoint and add a solution of 1% starch suspended in water. The starch complexes to the triiodide and forms a blue complex, and the disappearance of the blue is easier to see than the disappearance of the yellow. Word of warning, if you go too far and get the yellow too faint, there's not going to be enough triiodide to complex with the starch, and you won't get this magnifying glass effect on the endpoint. You just won't see anything. This is what it should look like when you add the starch. From here it should be less than half a milliliter of titration until you get to the endpoint, which is where this blue color goes away. Now the flask it will be cloudy because of the starch, and it may be not totally colorless, but what you're looking for is for that disappearance of that blue complex color. Here's another look at it. Your data analysis will be different for the standardization and the unknown determination, because only one of these is a back titration. The standardization is going to be done as normal. You'll calculate the number of moles of your primary standard that you added to your titration flask. You're going to use the balanced chemical equation to find out at the equivalence point how many moles of thiosulfate did you deliver with your burette, and then you'll use the volume delivered to find the molarity. The unknown determination is an indirect method, so you're going to have to do slightly more math. First, you'll calculate how many moles of iodate ion you added to the titration flask in the first place via your 50 milliliter burette. Next, you'll calculate the number of moles of thiosulfate that you delivered with your burette. The difference between these two numbers, the moles of thiosulfate, which is the same as the moles of iodate ion titrated away, and the moles of iodate ion that you started with, are the moles that reacted away when you added the vitamin C tablet to the flask, and this is described in your procedure. So you'll have a number of moles of iodate that reacted with vitamin C. You'll use the balanced chemical equation to find the moles of vitamin C that reacted, and then you'll use the molar mass of vitamin C to find the number of milligrams that were in the tablet originally. Again, this is a little more complicated than your normal data analysis, so make sure that you understand what you're doing before you leave the lab.